Alright, this lesson marks the beginning of our review of Unit 1, Part 1, which was all about systems of equations. So looking at number 1, remember we learned about substitution, elimination, different methods. Problem number 1 would be best done by substitution. I like to write the problem sort of sideways to help me think, but the first step of substitution is to get one variable by itself. That's why this one is great for substitution, because the y is already by itself. Once you have a variable by itself, you can substitute, because y equals this stuff. That means I can take all this and substitute it for y, like right there. So that means over here I will now have 2x plus 3 times parentheses equals -3, and inside that parentheses, those parentheses, I'll have -3x minus 8. Alright, so I take it and I substitute it right here. I always use parentheses because that will remind me to do the distributive property when it's needed. Okay, so I can just keep going now. Notice how this has all x's now, so I should be able to solve it. So this will become 2x, 3 times -3, so that's -9x, minus 24 is equal to -3. Combining my like terms, so that'll be -7x minus 24 is equal to -3. But then I would add 24 to both sides here. So that's going to give me -7x is equal to 21. It's -3 plus 24 is 21. And then you just divide both sides by -7 to get x by itself. So that's why the final answer will be x equals -3. Okay, and well, I say the final answer, but we've got x, we also need y. So we need to take this now and plug it back in, alright, for x, right here. If we do that, then we're going to get y equals -3 times -3, alright, because I'm plugging that in, minus 8. So that'll be negative times negative is +9 minus 8, so that's y equals 1. So now I've got my x and my y. If I want, I can write that as an ordered pair, -3, 1. Alright, so that is the solution to problem number 1. And so on my answer line, I would go ahead and write it as an ordered pair. -3, 1. Alright, now let's take a look at number 2. This one would be a good one to do by the elimination method. First of all, there are no variables that are anywhere near being by themselves. They all have coefficients. Also, they're all lined up nicely. So let's do the elimination method. Alright, now for elimination, we need opposites that cancel. So either the x's need to be opposites or the y's. Looking at the y's, these would be opposites if this were a 6 instead of a 3. So I can turn this into a 6 by multiplying by 2. Okay, if I do that, then this whole equation is going to become, let's see, so I'm going to have 24x plus 6y is equal to 32. Alright, you have to multiply everything. You know what, maybe I should put it over here. Now, meanwhile, the bottom equation doesn't have to change at all. So I've got negative 24x minus 6y is equal to 32. Now, I have opposites that cancel. Actually, I have more than I even needed because the y's cancel out, okay, and the x's also cancel out. So in this case, canceling out means 0. You know what I mean? Because 6 minus 6 is 0. Like, that's what's happening here. So the left side of the equation is simply 0. Now the right side is not 0. These are not opposites. 32 plus 32 is 64. So I get 0 equals 64. Now this is one of those special cases. And I'll just go ahead and tell you the answer here is no solution. This is a special case because both of the variables canceled out. Whenever that happens, you're either going to be left with a false statement like this or a true statement. Because this is false, false. 0 does not equal 64. That's how you know that it is no solution. Now, for instance, say if these had been opposites. They weren't. But let's say that had been negative 32 and positive 32. Then you would have had 0 equals 0. Now that is a true statement. And if you got a true statement, then that would be infinitely many solutions. Okay, that's when you get a true statement. But in this particular case, we got the false statement, so we put no solution. Alright, let's go on to number 3. Alright, we need to graph this thing. Let's color coordinate this. So first I'm going to graph this guy. Alright, now you're going to start by graphing the related equation y equals negative 2x minus 4. Okay, we're just graphing this line, which we would start at negative 4 and then go down 2 over 1. So start at the y-intercept, which is negative 4. That would be right here. Now this slope of negative 2 is like negative 2 over 1. So that means down 2 over 1. And we can just do that over and over again, down 2 over 1. And we can make more points on the left side by going up to left 1, like this. Okay, up to left 1. Alright, so these are the points. Now, we have to be careful before we draw the line, because sometimes it's dotted and sometimes it is solid. When it has an equal to line, when it's less than or equal to, or greater than or equal to, you draw a solid line to show that the border is included in the solution. So this does have the or equal, so we will definitely use a solid line. So it'll be like this. Okay, solid line. Now, let me make it blue so it matches. Alright, now let's go on to the other one. To make it longer. Now, the next one, x is greater than or equal to negative 2. We'll do this one in pink. Alright, well we will, oh yeah, wait, I almost forgot. The shading. Because this is an inequality, we need to do some shading. This is less than or equal to. Because we need to be in the area that is less than or equal to this line, you should be asking yourself, well, will the solutions be above or below this line? Well, clearly less than should be reminding you of the word below. We need to be below this border. So do not just shade in this entire thing. Just do a little bit of shading, sort of like this. Alright, this is the below side of the line. So I'm just going to put a little bit of shading down here to remind me that this is the proper side of the line to shade. Alright, but we're going to wait until we get a little bit more information before we do the whole graph. Okay, now the next one. When you see a tiny graph, tiny equation like this, the related equation, of course, is x equals -2. This tiny equation is a special case. Is this vertical or horizontal? This is a vertical line. Alright, look, x equals a number is always a vertical line because all of the x's will have x values of -2. So we will draw a vertical line at -2. Okay, so that would look like this. Alright, there's a vertical line at -2. Okay, this again will be solid because it's or equal to. Now the shading. A vertical line. This is normally we do above and below, like that last one we had shade below. A vertical line has no above and below. That's why we're dealing with x values, where we do left, right. So greater than -2, x values greater than -2 will be on the right. So again, we will not shade all crazy shading in half of the graph. We will just put a little bit of shading on the right hand side of the graph. Alright, one more equation, inequality. Let's do this one in green. Yeah, I'll do green. And this one will be horizontal. Okay, we're talking about the related equation y equals -3. Just like x equals a number is a vertical line at that number, y equals a number is a horizontal line at that number. So we need a horizontal line at -3. Alright, except for this one is going to be dotted because it's not or equal to. Okay, so there's your y equals -3. Now to make it y is greater than -3, we need to shade. Clearly, this is going to be an above situation. Above. Alright, so we will shade above like this. Alright, so the solution area, which we will shade in completely, is the area that satisfies all three of these inequalities at the same time. So we need to be below the blue line, alright, which puts us over here. But then we need to be to the right of the pink line, which puts us in this wedge right here. But then we need to be above the green line, which puts us in this tiny little triangle. So we need to go ahead and shade that in, because that is the true solution here. Okay, so that yellow piece I just drew, that is the solution region. Alright, so that is the graph of all the solutions. Anything in that little triangle is a solution. Now they're also asking us to list one possible solution, so we just need to pick a value that's in here, or at least on one of the lines. Let's see. For example, negative 1 comma negative 2 would be right here on the line. So that would be valid. So negative 1 comma negative 2 would be good. What else? Alright, negative 2 comma negative 1 would be right here. That would be part of the solution. I mean, it's on the line, but that counts. Alright, anything in this triangle or on a solid line. I wouldn't say negative 1, negative 3, because that would be on a broken line, and a broken line is not part of the solution. But say negative 2 comma negative 1, that would be good as well. Alright, and there are others, but you get the idea. So that is how you do number 3. Let's go on to number 4. Alright, in this problem we're supposed to find the maximum and minimum values of this objective function for the given feasible region, right? This shaded area here. This is the objective function. And so the max and min will occur at one of these vertices. So let's start at this one, 10 and 70. Okay. If I substitute 10 for x and 70 for y, that gives me one possible profit. Is P standing for profit? Probably. So let's see. So that would give me P equals, alright? So I'm just doing the 2x plus 3y. But in this case, that's 2 times 10 plus 3 times 70. Okay, and that equals, that's 230. Alright, so we just need to do that over and over again for these other points. So now let's do this one. So that would be, 2 times 60 plus 3 times 80. Alright, that's 360. Alright, the next point down. Alright, so it's 2 times 100 plus 3 times 60. And that gives 380. Alright, so that brings us to this one. Well, 3 times 0 is 0, so I can ignore that. So 2 times 80 is 160. Okay, so that's that one. So that just leaves one more, alright, which will be 2 times 40, alright, plus 3 times 10. Alright, look, 2 times 40 is 80. 3 times 10 is 30. So that's 110. Alright, so we're looking for the maximum value and the minimum value. You can probably see that the maximum value of 380 is right here. Now the minimum value is 110. Okay. Alright, so let's break it down. The maximum value of 380 occurred at the point 10, 60. I mean 100, 60. The minimum value of 110 occurred at the point 40, 10. Alright, I think that's it for this problem. That's all they wanted. That's how you do the whole max and min thing. Just remember. Word problems. Okay, as far as defining your variables for number 5, if you kind of look at the end of the sentence, how much does it cost members and non-members to attend the exhibit? That really lets you know what the variables need to be. All right, we can let X be the cost for members, and we can let Y be the cost for non-members. Now, the equations, writing the equations is really easy for a problem like this because the equations almost write themselves. I mean, look at this. Using the variables on which we just decided, it says 3 members. All right, so that's 3x, and 3 non-members, so that'd be 3y, pay a total of $105. So there you go. That's one equation. All right, how easy would it be to write a second equation from this in the same way? All right, see if you can guess what it will be. All right, if you were thinking 5x plus 3y equals 135, then we're thinking the same thing. I would definitely suggest elimination method instead of substitution. The variables are all lined up, and look, everything has the coefficients on it, so so don't do that. I'm going to see if I can just copy this real quick. Drag it over here. Okay, so look at those y's, man. We can make them opposites very easily if we just if I multiply the bottom equation, say, by -3. Okay, if I multiply these by -3, you know what? Maybe I'll do it this way. All right, say if I multiply this bottom equation by -1. My goal is to make the y's opposite, okay? If I multiply everything here by -1, then I'm going to get -5x minus 3y is equal to -135. All right, I just made everything negative. But the point of doing that was now the y's are opposites and they will cancel. So that will leave me with -2x equals -30. So dividing by -2, all right, that is going to give me x equals 15. Alright, so fine, x equals 15, that's the member price. Now the non-member price is the y value, so I need to plug this back in to one of the original equations. It really doesn't matter which one I use. Say if I use the 5x plus 3y is equal to 135 one. Then with x being 15 now, this becomes 5 times 15 plus 3y is equal to 135. Okay, 5 times 15 is 75. Okay, plus 3y is equal to 135. You could subtract 75 from both sides. So that'll give you 3y equals 60. 135 minus 75 is 60. Of course, we will just divide by 3 now. Alright, so that's going to leave y is equal to 20. Okay, so there it is, 15 and 20. So the cost for members is $15. Whoops, $15. And the cost for non-members is 20. Alright, let's try number 6, see how we do. This one is slightly different, but still the variables. If you look at this last sentence, how many of each ticket were sold? Okay, how many of each ticket? So let's see, that means there's two kinds of tickets. Looks like there's adult tickets and there's student tickets. So we can let X be, it says how many, so I'll let X be the number of adult tickets. And Y can be the number of student tickets. Okay, now let's set up the equation. Now, this is different than the last one, those ones where the equations just sort of wrote themselves. We have to think about this slightly, because what we have here is we have a quantity equation, and then in this case we have a money equation. Now the quantity equation is very simple. How much? Okay. We have some adult tickets, we have some student tickets, but it says 560 tickets were sold. Alright, total of 560. These are the two different kinds, so that equation is going to be very simple. X plus Y has to equal 560. Alright, the two kinds have to add up to the total, 560. Then there's the money equation, alright, where it says how much money for each kind. So adult admission is $7, alright, that's X. So $7 per adult ticket, so that's 7X. Student tickets are $5, so $5 per student ticket, alright, Y is student tickets. And the total amount of money is $3,500. Alright, so that's your money equation. $7 per adult, $5 per student, total of $3,500. Okay, I would recommend doing substitution on this problem. You could do elimination again, but substitution would work pretty great. Here's the idea. I would set it up horizontally, sort of like this. We need to get one of these variables by itself. It really doesn't matter which. So I could subtract Y from both sides, say. So that'll leave me X equals 560 minus Y, say. So then I could take this and substitute it in for X right here. So that's going to give me 7 times 560 minus Y. Alright, I'm here so far. Plus 5Y is equal to 3,500. Got to do a little distributive property here. 7 times 560 is 3,920. So this is 3,920 minus 7Y plus 5Y is equal to 3,500. So 3920. So I'm just combining like terms now, putting those together. That's negative 2y equals 3,500. Let's subtract 3,920 from both sides. Alright, that's negative 420. Okay. So that's going to give me negative 2y is equal to negative 420. Dividing by negative 2 on both sides, that's going to give me y is equal to positive 210. All right. All right, so $210 student tickets, because I'm pretty sure that's what Y was, student tickets. All right, and now all we have to do is plug that back into one of the original equations. Let's use the x plus y equals 560. Okay, so looking at this, x plus y equals 560, but y is 210, so that's x plus 210 is 560. Subtract 210. All right, so x is going to equal to 350, and that is the number of adult tickets.